Okay, can you keep it down so we can start, please? Okay, so today we're going to go through another integration technique, trigonometric substitution. Next week, we're going to do hyperbolic trigonometric substitution. And then the last integration technique will be partial fraction decomposition. Okay, so then that will be it for the integration techniques. Then we're going to be looking at the applications of integration for the remainder of the semester. Okay, so just to list out what we've done so far. So we've done U substitution, we've done integration by parts, we've done trig integrals. Okay, so today we're going to do trig substitution. Okay, then we're going to look at hyperbolic trig substitution. Okay, and finally, we're going to look at partial fraction decomposition. So basically, this is your scope for the class test 1. So once we're done with the partial fraction decomposition, your class test 1 will be on these integration techniques. Okay, so U substitution we're done, integration by parts we've done, trig integrals we've done, trig substitution, we're going to cover that this week. Now, note when we do trig substitution, once we've done the substitution, the problem becomes a trig integral. Okay, so it's a way of converting between problems. So we've got a problem, we do a trig substitution, then it becomes a trig integral problem. So all of the stuff we looked at last week on solving trig integrals, we're going to need that for this week for the trig substitution. Okay, so just keep your notes open for that. Any questions for the test breakdown? You're all good. Okay. Okay, so this week, trig substitution. So we start off with 3 cases that we're going to be looking at. So if you see an integral that contains these 3 cases or something like that, then you should be using a trig substitution. Okay, so it's a way of identifying when we use this and when we don't use this. Okay, so case number 1 is if your integral has the following. So we have the square root of a squared minus x squared. So something like that. Okay, so something with a squared minus x squared in the root, then that is going to be case 1 for trig substitution. So if you see this, you should use this method. Now, the substitution we're going to make for this case 1 is the following. So we're going to replace x, wherever we see an x in the problem, with x equals a sine theta. Okay, so we do the replacement, then the problem with the roots becomes a trig integral. Okay. Notice that in the root there is a squared, and then on the right there is just a. Okay, so whatever number is there, you take the root of it to get a. Okay, everyone see that? So we got a squared in the root. So if that was 16 minus x squared, then on the right it will be 4 sine theta. Okay, please keep that in mind. Okay, so that's case 1. Case 2 is if we have the root of a squared plus x squared. So instead of the minus, it's now a plus. In this case, we do the following substitution. Wherever we see an x, we're going to put a tan theta. Okay, and again, a squared there, and we have a on the right. Okay, and finally, case 3, this will be the root of x squared minus a squared. Now here, please put a little star so you don't confuse number 1 and number 3. Number 1 is a squared minus x squared. So the a squared, the number comes first. In case 3, the x squared comes first. Okay, please do not mix those up. And then for this one, we're going to make the substitution. X is equal to a sec theta. Yeah. Again, just put a little star here so you don't mix up that ordering. So a squared comes first, we use sine. X squared comes first, we use sec. Okay, just note these will not be given to you. You will have to learn these. Okay, so given the roots, what substitution you need to make, you need to know that. Okay, also something you need to know is your trig triangle. So remember this from way back when. If we have theta here, then on the opposite side, right, that's the opposite. On the adjacent side, that's your hypotenuse, your adjacent. And then on the other side, that's your hypotenuse. Okay. So please, if you forgot your identities with sine, cos, and tan, opposite over adjacent, opposite over hypotenuse, and so on, please make notes of that. Okay, we will need to know those. Okay, so let's have a look at the first example. So here we have the integral of root 9 minus x squared all over x squared dx. Okay, so we look at this. Remember, the first thing you always look for is a u substitution. Okay, so forget we're doing this specifically. First thing, u substitution. If we let u be that inside part, 9 minus x squared, du will be minus 2x. That doesn't really help us. We got an x squared at the bottom. Okay, so u substitution, that's not going to work. Can we do integration by parts? Not really. There's nothing easy to integrate, nothing really easy to differentiate. So we move to the next thing. Is it a trig integral? No, there's no trig functions. So we skip that. We go to the next thing, which is trig substitution. Okay, so whenever you get a problem, please go through that list from top to bottom before you skip right to this one. Okay, because a lot of the times u substitution or integration by parts is a lot easier than trig substitution. So maybe you can solve it with the easier method. So, save yourself the trouble, do the easier one rather than doing the more difficult one. Okay. And we'll see that later with a couple of examples. But here we can't do any of those, so we go to trig substitution. So in the roots, we have 9 minus x squared. So which case is that going to be? 1, 2, or 3? 1. Okay, what is a going to be? 3. Good. So we're going to substitute x is equal to 3 sine theta. So wherever we see an x, we're going to make the substitution. And then we need dx, so we need that as well. So here dx, that will be 3 cos theta d theta. Once we've got that, we can then substitute. Yeah. And then after all of the substituting, we'll see we have a trig integral that we need to solve. Okay, so let's do that. So in the top, we're going to have root 9 minus x squared will become 9 sine squared theta. In the bottom, we have x squared. That's going to be 9 sine squared theta. Okay, and then dx, that's going to be 3 cos theta d theta. Okay, everyone clear on the substitution? All good. Okay, so now we can simplify, and then we get a trig integral. So in the top, we have a 9 and a 9 there, so we can take that out of the root. That will become a 3. 1 minus sine squared, what will that be? cos squared. And then we have the root. So that will just be cos. So the top, that will be 3 cos theta. And then from the dx, we got another 3 cos theta. And then in the bottom here, we just have the 9 sine squared. We can leave it there. Okay, in the top, we've got 3 and a 3. That will be a 9. That cancels with the 9 at the bottom, so we can get rid of those. And then in the top again, we've got cos squared divided by sine squared. That's going to be cos over sine, cot. So it will be cot squared. Okay, so this is a trig integral. So all of this stuff from now on is what we covered last week. Okay, so after all of the simplifying, all of the methods from last week now come. So integral of cot squared, what do we do? Yeah, check your notes. We did it last week. With the tan squared and the cot squared, it was one of the examples. Sorry? Cosec squared minus 1. Good. Okay, so this will be cosec squared theta minus 1. So we use the trig identity. So please check your notes from last week. We covered this and the one with the tan squared. So we can split this into 2 problems now. So this will be the integral of cosec squared and then just the integral d theta. Okay, integral cosec squared. What's that? Yeah, minus what? Minus cot. Good. Okay, and then the integral d theta, that's just theta. Okay, so we've solved the trig integral now, but remember we did the substitution of x for this 3 sine theta. So we can't leave our answer in terms of theta. We need to now write the answer in terms of x. Okay, so we now need to write the answer in terms of x. Okay, and this is where we're going to use our triangle from earlier. Okay, so from our substitution, we know that x is equal to 3 sine theta. We can rearrange this a little bit to write sine theta is x over 3. Okay, a little bit of rearranging. But from this fraction or from this ratio, we now get opposites and what's the bottom one? Hypotenuse, yeah. So we can fill in the triangle with the opposite and the hypotenuse. We can find the adjacent. Once we have all 3 sides, we can then find cot. So let's draw a triangle. So we have theta over here. From the ratio with sine, we see x is on the opposite. 3 is on the hypotenuse, so we put a 3 there. And then the adjacent is just what's left over from Pythag, right? We've got opposite, we've got adjacent, hypotenuse, now we need adjacent. That's going to be root 9 minus x squared. Right, it's just trig to find the missing side. Now that we have all 3 sides, we can find all of the ratios that we need. So cot theta as a ratio will be something over something. Well, what will it be? Okay, what's tan? Opposite over adjacent. So cotan will be adjacent over opposite. Yeah, and we just fill it in. So we know adjacent, we know opposite. We can just fill that in there. So the adjacent one, we know. The opposite, we know. So cot, that's done. Okay, what about theta? Well, we know sine theta is x over 3. So how do we solve for theta? Someone said it? Sine inverse. Yeah. So if sine theta is x over 3, then theta is sine inverse of x over 3. So this will be minus sine inverse x over 3. Okay. And everyone following along with the steps? Okay, so here's step 1. We make the substitution based on whatever case it is. Okay, step 2, you substitute all of that in, you do your simplifying, and then you'll end up with some trig integral. So that will be step 2. Okay. And then once you've done your trig integral, okay, from whatever we did last week, you end up with something with trig functions and theta. Then you can use this triangle on the side there to write it in terms of x. So that will be your step 3. Okay, so 3 steps. Substitute, solve the trig integral, and then finally use the triangle to write it in terms of x. Okay, just the 3 steps. Any questions for this first one? Okay. Pretty simple. Okay. Another example, number 2. So we have the integral 1 over x squared root x squared plus 4. Okay, so again, we go through the checklist. Can we do a u substitution? Not really. If we let u be x squared plus 4, du will be 2x, but we've got an x squared at the bottom, so that doesn't really help us. Integration by parts, not really. You can't split this up nicely, so we're not going to do that one. It's not a trig integral, so we can't do that. But we do see x squared plus 2 squared, right? X squared plus 4. So we can do a trig substitution. So if it's x squared plus a squared, we go up a little bit. X squared plus a squared, that's going to be case number 2. Okay, and a will be 2, because we had the 4 there. Okay, so we make the substitution. X is equal to 2 tan theta. Okay, so wherever we see an x, we put the 2 tan theta. We also need dx, so let's find out what that is. Okay, derivative of tan. It's x squared, yep. Okay, please remember your derivatives, right? Tan goes to sec squared, all of that, so that you can find your dx. Okay, let's just go through that quickly. Okay, so derivative of tan, sec squared, we know that. Derivative of sec tan. Okay, good. I think most of you know it. Okay, so let's substitute. Wherever we see an x, we're going to put 2 tan theta. So at the bottom there, x squared, that will be 4 tan squared theta.